Alright, so in this video, I'm going to derive the expression for rotational kinetic energy. Uh, Before we get into the formal derivation, let's see if we can deduce the expression for rotational kinetic energy just by looking at the analogy between linear and angular quantities. So we've seen this table in class. So suppose you have an object that's starting from right here, point A, goes to the point B. Um, the actual distance that is covered along the circle is the arc length s, and its location at B can be specified by using the angular position theta, as we've seen below, as we've seen in class before. Um, the velocity of the object uh, can be measured. The linear variable for that is v, and the angular variable for that is omega. And the acceleration of the object, the linear variable is a tangential, and the angular variable is alpha, right? Now we can continue to add things to this table. So inertia of an object in the linear world, that's measured by the mass of the object. And which quantity measures the inertia of an object, the rotational inertia of an object? The answer is I, as we learned yesterday, right? All right, so that's one addition that we can make to this table. We can now immediately make another addition to this table, kinetic energy. So kinetic energy in the linear world is half mv squared. Can you guess what the expression for kinetic energy is going to be in the angular world? See if you can figure this out first, and then uh, see how I do it. So the kinetic energy is half mv squared. So entirely by analogy, you can write down the kinetic energy expression as half I omega squared. How did I get that? So the analog of mass is I, and the analog of phi is omega. So just by analogy, you can write down the expression for kinetic energy as half I omega squared. All right, that's really all that you need to know as far as this course is concerned. But in this video, I'm just going to show you why the expression for rotational kinetic energy is half I omega squared. All right, consider this disk that is rotating. It doesn't have to be a disk, it can be any shape. Um, so consider this disk that's rotating about an axis through its center, which is point O, and the axis, so that this disk is rotating, actually I should say disk of mass m, so rotating uh, about an axis through its center, the point O, and the axis is perpendicular to the plane of the disk. Okay, all right, now this, and let's say that the angular velocity is omega. So basically you've got a disk of mass m, and let's also say that the radius is r, and it's rotating about an axis through its center perpendicular to the disk with an angular velocity omega. All right, now we want to find out the kinetic energy of this disk. Now the only formula we know for kinetic energy is half mv squared. Will that work here? What is the velocity of the center of mass of the disk? Uh, so when we have had extended objects before, we've just considered the velocity of the center of mass of the object. So what is the velocity of the center of mass of this disk? Um, it's clearly zero, right? Because the disk is at rest, but it's rotating about its center of mass. So half mv squared will just give you zero, and so it's clearly not the right way of getting the kinetic energy, because you know that the disk must have some kinetic energy if it's rotating. But our formula half mv squared just seems to indicate that um, the disk has no kinetic energy because its velocity of its center of mass is zero. So that's not a useful approach. So let's see if we can figure out the kinetic energy of this disk some other way. So we're going to use the same reasoning that we used when we derived the expression for rotational kinetic energy, rotational inertia. What we did was we broke this object up into small segments, right? And let's say that this segment, for example, has a mass. Let's make some room here. Has some mass of, oops, delta m1, and it's at a distance r from the center, r1 from the center, right? It has a mass delta m1 and has a distance r1 from the center. Let's see if we can find the kinetic energy of um, this little segment over here, and then we'll find the kinetic energy of every segment on the disk and then add them all up to find the total kinetic energy of the disk. So that's the plan here. All right. Now, so and in order to find the kinetic energy of this small segment m1, delta m1, we will use the simple formula for the formula for kinetic energy that we're familiar with, which is half mv squared. So we're going to use that formula. All right. So what is the kinetic energy of this little segment which has mass delta m1? So for that I need to know the mass, which I already have. It's delta m1. I also need to know what velocity, what is the instantaneous velocity with which this mass is moving. So this mass is describing a circle like this, just this m1. It's describing a circle like this, and its instantaneous velocity is in the tangential direction, right? Let's call that v1. So what is the v1? So every part of this disk, the whole disk, is rotating with angular velocity omega, right? So can you tell me what v1 is going to be in terms of r1 and omega? So v1 is going to be r1 times omega, right? All right, so we found the velocity of this little segment, um, delta m1, and so its kinetic energy would be half delta m1 v1 square, which is half delta m1 r1 square omega square, right? Okay, so we've successfully found the kinetic energy of one little segment. So I can repeat this exercise for other segments. Let's say I've taken another one over here, which has a mass of delta m2, and it is at a distance r2 from the center, and its mass is delta m2. So the kinetic energy of that I can find using the same formula. It would be half delta m2 r2 square omega square. So what is the kinetic energy of the entire disk going to be? So for that, I'd have to break up the whole disk into segments like this, calculate the kinetic energy of each segment, add them all up. So the total kinetic energy of the entire disk would be the sum of all of these. So half delta m1 v1 square plus half delta m2 v1 square. So I'll just do it like this, v2 square and so on. I'll just plug in what we had for v1 and v2. So the kinetic energy would be half delta m1 r1 square omega square plus half delta m2 r2 square omega square and so on. Okay, now let's just imagine this is a large sum, right? So uh, there are going to be many terms in this sum for all of the pieces that I've broken up the mass into, the disk into. Let's just imagine factoring out the 1/2 from the left side. Then we have all of these terms in the sum. What are they going to be? So delta m1 r1 square omega square, and then delta m2 r2 square omega square. And let's just imagine factoring out the omega square at the other end like this. So inside the sum, I'm just going to leave delta m1 r1 square plus delta m2 r2 square and so on, right? So all I've done is just slightly rearrange this, all the terms here. The half and the omega square are common to each of these terms. So I factored both of them out, and just for fun, I've written the omega square at the end and the half in the beginning. All right, so now let's see what this is. What is the quantity inside the brackets? So delta m1 r1 square plus delta m2 r2 square plus delta m3 r3 square, where these are all delta m's are all the pieces, the masses of the little pieces that you've broken up the disk into. Does this expression ring a bell at all? This sum is nothing but the rotational inertia of the object. So I'll just write it like this. So this is half summation over I delta mi ri square omega square. And so this sum is nothing but the rotational inertia of the object. So you get kinetic energy, rotational kinetic energy is half I omega square.